everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Dr. Bassam Alrifaee. I hope I pronounced it correctly, who is a senior researcher and a lecturer in the Department of Computer Science at RWTH Aachen. Although I just discovered he's going to move soon, so probably he will be able to tell you better the new, the new affiliation and everything. At Aachen, he's the founding director of the Cyber Physical Mobility Group. In his research, he focuses on distributed predictive control, service-oriented architecture for control systems, and applications of these first 2 points to connected and automated vehicles, especially in the context of mobility system. He earned his diploma in computer science from the Technical University of Ilmenau and his PhD in mechanical engineering from Aachen. Today's talk is going to be about the work in his group, and the title is Multi-Agent Decision-Making in the Cyber Physical Mobility Lab. I'm personally very excited to hear more about it. Bassam and I had plans to have this talk for the past year, and now finally it happened, and therefore I give you the stage, Bassam.
Yeah, thank you so much, Joelle, and I am very happy to be here. Thank you for having me. And now I start my screen. I hope you can see now my slides.
Yes, yes.
Yes, this is perfect. Yeah, this is a great opportunity to present you with my work. I was waiting for this opportunity for the last year. And in this talk, I would like to give you an overview of my work in multi-agent decision-making in my cyber physical mobility lab. And as you mentioned, and as you noticed, some people here are from my future institute in Munich. So this is one of my last talks with my affiliation at RWTH. And I would like to start this talk by stating that this work, which I'm going to present, is the work, of course, of my group. And I started the group at 2017, and 2 of my group members have completed their PhD this year and last year. And for the transition also, I am looking for further students, PhD students, or postdocs. And one of my PhD students, Patrick Scheffer, is also here in this talk, and he could also join our Q&A session and answer some questions. Also, Amin Mukhtarian is in this talk, and he will assist me in presenting something very cool, which I am going to tell you in some minutes. So I would like to start this presentation with this video. This is taken from our Cyber Physical Mobility Lab. What you see here are our small-scale vehicles. We call them Mi cars, Mi like the Greek letter mu, which is pronounced in Greek Mi. And the area here is around 4 by 4 meters on the outer ring here. This is our Autobahn. This is our highway, and with highway entrances and exits. And in the middle, we have our city intersection. So the vehicles here get the task to drive as fast as possible and to be safe. So at the same time, there is a trade-off here between safety and efficiency. And as you see, the vehicles manage to avoid each other and to drive very fast. So how we can implement such a cool scenario? For this, we need some elements. We need the well-known scheme of sense, plan, act. But in addition, we need also things which we cannot see directly in this video, like the software architecture or the human autonomy interaction. So in this talk, I am going to focus today on distributed predictive control, service-oriented architectures, and real-time experiments. Today, we will skip the localization part, and I would like to start with the distributed predictive control. For this, I have one slide, very quick introduction to predictive control, as assume many of you are very familiar with predictive control. Let's look at this example. So we have here a vehicle driving from west to east with a constant speed, and its task is to follow the white line. For this, we measure the distance between the vehicle position and the white line, and we use the steering angle to get back to the reference trajectory to the white line. For this, we could use classical control. This is similar to drilling a hole in the vehicle floor and looking where is the reference trajectory and to drive there. The other way is to use predictive control, for example, MPC. And for this, we look outside of the windshield. We tell the vehicle to not drive to the tree, to drive on the street. But if a lane is blocked, we need to avoid it and stay on the street. This is a very quick introduction to predictive control. And now I would like to get you into the network thinking. And for this, I have an example and a game. So let's start with the example. The example is of pedestrian walkings. Everybody of you have experienced this or observed this, especially in crowded city centers. For example, it was amazing for me to observe this effect at the Shibuya crossing. So two pedestrians approach each other, avoid each other once, avoid each other twice. Sometimes they manage to resolve this conflict. And imagine how is this if it scales to n pedestrians, how they manage to avoid each other and to go efficiently, for example, at the Shibuya crossing from the one side to the other. This is the example. And the game is a very simple game. If you had a course on game theory, for sure you know this, this game. So the game is very simple. Choose a number between 0 and 100. And the winner of you is going to be the closest to the half of the average. And I conducted this game several times in my courses. And in general, the result is around 12.5 of the winner. Why? Because there is the level 0 thinker who says any number between 0 and 100. There is the level 1 thinker who says we are looking for the average. So I'm going to say 50. And there is the level 2 thinker who says we are looking for the half of the average. And this is going to be 25. And unfortunately, the majority of the people are level 2 thinkers, but there are level 3 thinkers who say, okay, we are looking for the half of the average. And if most of the majority is going to say 25, the half is going to be 12.5, and you are going to win in the first round. Why I showed this example and this game, it is for to motivate you, to get you to the network thinking and to show you that the decision quality of individuals is affected by the decisions of others. In this game, you need not only to think about yourself, but also to think what the other players are thinking, because they want also to win. I hope I got you with this example and with this game into the network thinking. And now let's get more technical. In terms of technical terms, we talk about network control systems, NCS. And in some areas, they are called connected systems. For example, we talk about connected and automated vehicles. And in general, NCS communicate and interact. And why do you use them in autonomous systems? We use them to improve perception and decision-making. And using NCS, we impose several challenges we address with our research, as you see here again with the 4 topics I showed you in the content. And here are two examples of improvement of perception and decision making. On the left-hand side, this is a very typical example of improving perception. Vehicle number 1 is driving from south to north and 3 from north to south. There is a pedestrian trying to cross the street, and there is a standing vehicle number 2. The sensors of vehicle number 1 cannot detect the pedestrian. The sensors of vehicle number 3 can detect, and vehicle number 3 can tell vehicle number 1, be careful, there is a pedestrian, don't collide with the pedestrian. On the right-hand side, we see a typical example of decision-making. This is the intersection example. Vehicles have the task to drive as fast as possible through the intersection, and of course, they need to drive safely. So this is the trade-off here again between safety and efficiency. In our research, or in this talk, I'm going to focus on the decision-making and the challenges we address in NCS decision-making. So on the method level, we look at enhancing safety and efficiency while reducing the computation time and communication effort, and considering mixed systems, for example, human autonomy interaction. So if you think of human autonomy interaction, we need to take care of the interaction between human and autonomy in the vehicle, outside of the vehicle, and between connected and automated vehicles and human-driven vehicles. So we apply our methods in applications, and we use optimization methods like applications like go-to formation, road intersections, and vehicle racing. I'm going to show you some examples of our applications in a minute, so stay tuned to it. So how to handle NCS? First, we look at the classification of NCS. I did this classification based on the literature. So there is, in general, a classification to systems, controls, and algorithms level. So if we look at network control system, we can classify it in coupled or decoupled dynamics. So decoupled dynamics are like vehicles on the road. If a vehicle accelerates, the other vehicles are not going to automatically accelerate. On the controls level, we have the networked MPC, and the advantage of networked MPC is that we can take the plans of agents into consideration, so of all agents, and because of the prediction nature of MPC. And networked MPC, we can classify into centralized, distributed, or decentralized. In this talk, I'm going to focus on distributed MPC, but first, just a quick introduction to centralized MPC. So in centralized MPC, we have a center who collects the data, computes the optimal values for the agents, and send them the values, the control inputs back. So this is not applicable in practice because we have high computation time, and we have safety hazards because we have single point of failure. But we compute centralized MPC because we use it as a benchmark for comparing different distributed MPC strategies, which I am going to show you in the next slides. So in distributed MPC, we study cooperative and non-cooperative DMPC. Each of these topics was the PhD thesis of one of my PhD students, and I start with cooperative. In cooperative MPC, usually we decompose the centralized MPC into smaller optimization problems. That means we consider a centralized problem in this example in 1 for 1 and 2 and 4. So in each agent, for the agent itself, and its direct neighbors, and of course the conflict between the neighbors we consider as well. And doing so, each agent just considers hypothetical plans of its neighbors, because I consider the plans of two. So in one, I plan for two, and two also plans for one. But in one, I apply, as it's common in MPC, only the control inputs computed in one. So there is a problem in this scheme because we have local system knowledge. Let's look at this example. So the perspective of agent one is agent one sees agent two and agent four. And the perspective of agent two is that agent two sees the agents 1, 3, and 4. You see here that agent one doesn't see agent 3. So while agent one is making a plan for agent two, it doesn't consider agent number 3, but while 2 is making decisions for itself and its neighbors, it sees the agent number 3. And this means that the predictions made in 1 for 2 are different from the predictions made in 2 about itself. And in simple words, this maybe sounds a little bit complicated. In simple words, what I think about yourself now, you think about yourself also now. And we call this property the prediction consistency, and it's very important in network control systems to ensure feasibility and also stability of NCS. So in general, how we can handle local system knowledge, we can, in general, in literature, find approaches using sequential and or iterative approaches. In my group, we developed a method using synchronization, and I'm going to present this method to you just in 1 or 2 slides. So the idea is very simple. Each agent plans from its local knowledge, and in the next step, we are going to synchronize the plans. So what I think about myself and what I think about you and what you think about yourself, we are going to synchronize. And a simple synchronization is, for example, calculating the average of the plans. And we were able to prove that our synchronization-based DMPC converges to globally feasible plans and apply it to connected and automated vehicles. So now let's look at non-cooperative DMPC, which is very interesting in terms of computation time, because there we have some potential for reducing computation time. So in general, what is the non-cooperative DMPC? It's again a decomposition of the centralized MPC into smaller optimization problems. And we consider only the own objectives and own constraints in our optimization problem. But additionally, we consider the coupling objectives and constraints with the neighbors. So we believe what the neighbors tell us. So that's why it's a greedy algorithm. I'm going to showcase this in an example in a minute. And we use the communicated plans from the neighbors, which are in nature time delayed. So let's look at this example to understand it much easier. So in this example, we have 2 vehicles driving towards each other. Vehicle number 1 driving from west to east and 2 from west to east, and they are placed perfectly symmetrically around the y-axis. And they are driving exactly with the same speed, and the reference is exactly the same. It is the straight line towards each other. So if the vehicles would continue, they would collide at the origin. now vehicle number 1 tells vehicle number 2, this is my plan. 2 tells 1, this is my plan. And both vehicles decide to replan to avoid the collision with the other vehicle. And this leads to a collision in the prediction. And now, because this is greedy algorithm, each vehicle considers its own objective and constraints. Each vehicle decides to drive back to the reference trajectory. And again, they collide at the reference trajectory. Now, both vehicles swap plans, and again, they avoid each other, but they think they avoid each other, but they have collision. And this may continue to happen till we cannot avoid the collision. What can we do? What is the source for this consistency problem? So the source is the coupling graph. It contains cyclics, and it means that two agents, 1 and 2, consider each other exactly at the same time. So cyclics in coupling graphs lead to the loss of the prediction consistency. And if we look at the literature in general, there are solutions based on sequential or iterative approaches. And in my group, we look at a priority-based approach. So why we look at the priority-based approach? Because it gives us some structure we can utilize to improve feasibility, means prediction consistency, and we can use it also to reduce the computation time. So let's look at this approach. First, we assign priorities to the agents and assume the priorities are here the same as the node numbers. And we tell the agents to compute in sequence. So one after the other. So the priorities here are 1, 2, 3, 4. So the vehicles are going to, or the agents 1, 2, 3, 4 are going to compute one after the other. We are lucky because in general, network control systems are not fully coupled. And this means we can make use of the structure of the problem and reduce the computation time. And distributing priorities to the agents generates what we call a partial order. And in general, in math, a partial order can be converted into a topological order. And this is only possible if the coupling graph is a directed acyclic graph. And we could prove this mathematically, and this is true. And we were able also to show that our sequential PDMPC generates globally feasible plans, of course, if they exist. And here's an example how we reduce the computation time. Assume we have this NCS with the nodes 1, 2, 3, 4, and they are coupled in the way you see here. And we can directly see that 2 and 3 don't depend on each other, so they can compute in parallel. After 1 and 4, after 2 and 3. So we were able also to find an algorithm in the literature which solves this problem. It's called the Kahn algorithm. It looks at agents without incoming edges and put the node on the next level and delete the node and the outgoing edges and look again at the next node and so on. And in this way, we can generate a topological order. What else can we do to reduce the computation time if the graph is not fully connected? We can make use of this theorem, which was proven by Patrick, one of my PhD students. Minimizing the computation levels is equivalent to coupling graph coloring. So the graph coloring, this is a short introduction to it, is color a graph with the minimal number of colors such that if two nodes are connected, they have different colors, as for example, here. And we were able to prove that the number of colors is equivalent to the number of computation levels. So if you have 4 agents and want to compute, then we need to come in sequence, then we have 4 sequences. But if we find a minimal number of colors, then we can, for example, here reduce the number of levels to 3. And what else can we do to reduce the computation time? In many applications, we need to define a maximum computation time and allow the agents to find a solution within this time. So the agents need to find a solution within this time. And we use reachability analysis to avoid prediction on inconsistency. So if an agent considers the reachable set of the higher priority agent, then we don't need to worry about the prediction consistency, because we are going to not only consider the plan, but we are going to consider a set. Let's look at this example. We have 4 agents here. So if they would compute in sequence, we would have 4 computation levels. And if we make use of reachable sets, for example, here of vehicle 2, then vehicle 3 can compute in parallel to vehicle 2, and we can reduce the computation levels to 2 just by considering the reachable set of 2 in 3. This was a general introduction to the MPC, and now it's time for me to take a small break, very small break, and a time for you to think about the solution of this chess game. So you play white, and your task is to have a checkmate in 2 moves. So take some seconds to think about the solution. So I hope now you are thinking about the solution. While you think about the solution, you may think on the steps you are thinking of. Why I am showing this example? Because it's very similar to distributed predictive control. You need at the same time to have a model of the game. You need to consider not only your plans, but also the plans of the opponent. And this needs to be considered in real time. So you have limited time to solve this problem. And if you are curious about the solution, here is the solution. Move the bishop to d3 and the queen to c2, and you are going to win. I simulated this several times, so it's for sure. And now let's look at some simulations. On the left-hand side, we see a simulation of an intersection. The vehicles need to drive as fast as possible and also safely. And on the right-hand side, we see a very nice example we call go-to formation. It's very exciting. We distribute vehicles around the plane and assign the vehicles target poses. A pose is a position and orientation, and tell the vehicles to drive as fast as possible to their target poses, but at the same time they need to drive safely. So efficiency and safety are again here playing against each other. And as you see, we are able to implement this example using, of course, centralized MPC, but also using distributed MPC. Why this example is so exciting? Because it abstracts many applications in this area. In many applications, you can think of vehicles having arbitrary starting poses, and we have goal poses for them, and they need to get there as fast as possible, but safely. And here, even more exciting scenario is the vehicle racing. So the vehicles here need to compete to drive as fast as possible and to win around the track, but at the same time, they have to avoid each other. So again, here is a very interesting conflict between progress and safety. So it is competition between the vehicles, and also at the same time, they need to have some sort of coordination. So till now, I showed some simulations. They are exciting, but for me, they were not exciting enough. And that's why was my motivation to go to real-time experiments. So there is a gap between simulations and real world. In simulation, we can quickly test ideas. In real world is, I think, really more exciting, but it's also very expensive and takes a lot of organization and logistics. And if you run real world experiments, you know that maybe you have 1 day for testing, and the tests work the whole day, that don't work the whole day, and work maybe at the end of the day, and you spend a lot of time preparing, driving, logistics, and so on. So it's a lot of work, and that was my motivation to build the cyber physical mobility lab. So the lab vision is to see your ideas turning into reality very fast. So the lab is directly in the building. The PhD students can code and see that the simulation works, and go directly to the test bed and test their algorithms. So here are some features of the test bed. It's completely open source. If you have enough time and enough money, you can rebuild the test bed. So it costs around maybe 25 to 30,000 euros if you want to have 20 of the Mikas. And if you cannot afford this time and money, you can use also our remote access. So for remote access, you need only to have a web browser, and we run your algorithms completely on our server. We support also centralized and distributed computations. We have a deterministic computation model, and therefore we have reproducible experiments. And here, by reproducibility in experiments, I mean not the control, but the computation model is deterministic, which means that the computations are not random, so that we take care of the synchronization between the agents, we take care of the communication, and this leads to our deterministic computation model, which allows your experiments to be reproducible. So with the same initial conditions, with the same algorithm, if you run the same experiment twice, you are going to get the same results. Of course, we are looking here at the computation model and not at the dynamics. Of course, the dynamics are not deterministic. And we have a digital twin, which allows for seamless extension of our vehicles. We have 20 physical vehicles, but we can extend them with digital ones to unlimited number of vehicles. Here's our testbed architecture. So our focus is on coordination and decision making, but of course we have also modules for perception and for actuation, so that our architecture is built up in the well-known scheme of sense plan act. The message for you from this architecture is that our architecture is modular. So if you want to go to the testbed and replace, for example, the coordination, you don't need to touch the other modules. You can just take out the module coordination and put your code and see what happens. So now I introduce the ingredients of decision making of our testbed, and now you see how this scenario works. But now you see this scenario from the bird eye view. So as you see, the vehicles drive around, they are quite fast and they don't collide with each other. But how does it feel to be in one of these vehicles? I hope you can listen also to the sound. So they are really fast. So I cannot look for very long at this scenario. I get dizzy, and you can see how it feels also to have an accident, for example, with these vehicles. I calculated roughly that it feels like 150 kilometers per hour on an accident. It feels like 150 kilometers per hour, and that's in an intersection, so it's high speeds. So we studied how we can incorporate human-driven vehicles in our testbed, and in general, the interaction between CAVs, connected and automated vehicles, and HDVs, human-driven vehicles. And for this study, my PhD student, Patrick Scheffer, won the Young Research Award 23 of the ITSS Germany. So congratulations to him. And of course, I was telling you that we can that you can access the testbed remotely, and you need only a web browser for this. And this video shows on, maybe I can show it again. Yes, I can go back here. Yes. So on the left-hand side, we see the digital twin, and on the right-hand side, we see the webcam from the testbed. And here we see some of the graphs. And directly here, we can also go to the editor, and you can see your code, change your code, submit again, and see the results. So the remote access supports several modes. In one of the modes, you can develop your algorithms in simulations, and then submit your code. We get notified, and whenever we go to the testbed, we run your simulation and send you back the data and, of course, the recordings of the webcam. The other way is to ask us for a real-time access to the testbed and directly put your code and see what happens in the testbed. And I asked my PhD student, Armin Moktayan, who is in charge of this remote access, to have real-time access, and I hope it's going to work. I have slow internet connection here. Maybe it's going not to work smoothly, but for this you need to go to CPM remote and then you need to register. The registration is very easy. It's just putting email address and password, and then you have a login. So I am already registered. I am going to log in. So I am now inside. So you can choose between default project or create your own project. We have also some projects for learning programming, and we have also some projects for competitions. So I'm going to talk in a minute about the competitions. So I'm going here to start a session and request now a session on our server. And now I am on the server. I hope now it's going to work. So I am turning on the cam. Now you see live the testbed in Aachen. So I am now in Munich and accessing the testbed. I can also go here to the editor and see the code and edit it in C++. If you like, also you can change to dark mode or whatever you like. And I'm now going to start this scenario. I hope the internet connection is fast enough to let the scenario run. So what we see here on the left-hand side is the results of the simulation. And on the right-hand side, the vehicles driving in on the map in the testbed. So I think the internet connection is not fast enough to transfer here the camera images. So we stick to the video, and you know that now that it works and it looks like this. So here are some numbers about our outreach. So some people visit our website and rebuild also our lab. For example, at the the German university in Cairo, they started rebuilding our testbed, and some parts of the testbed are also rebuilt at other institutes. We are, of course, not the only group building such a testbed. There are several testbeds. That's why we joined our forces and started a survey on testbeds. And if you go to our website and put /testbeds, you see preliminary results of our survey. So if you have a testbed, if you run a testbed, please ask us to give you access to our table. So it's just a Google document table, and you can put the data of your testbed, and it's also possible to compare 2 or 3 of them, like you know it from Apple products and so on. So you are invited to contribute to this. Why we are doing this? Because we want also to make research in this area more accessible. And we are working also on an abstraction layer between testbeds. If you develop algorithms for a testbed, you can run them in a different testbed. And here's an example of connecting the testbed, the CPM testbed, with the IDS3C. Now at Cornell, but we did this work while Andreas Malikopoulos was at the University of Delaware. On the right-hand side, you see the planner, the motion planner implemented by Patrick Scheffer in Aachen. And on the left-hand side, at the top, you see a view of the CPM lab, and at the bottom, the IDS3C. And we connected the 3 test beds, so the same code can now run in simulation and also in both test beds. Now I'm going to start the clip. Now we see 3 vehicles are driving towards the roundabout. Vehicle number 1 and 2 now coordinate to avoid collisions. and drive on the street, and you saw exactly the same behavior in both test beds. You don't need to consider special software of the test beds. There is an abstraction layer. If you write the code for one of the test beds, you can run the same code in the other test bed. And we are running a motion planning competition we call Cyber Physical Mobility Olympics. My PhD student, Amin Mukhtayan, is in charge of this. He is also here with us in the Zoom meeting. So you need to develop planning algorithms for real-time traffic scenarios. So we provide you with the traffic scenarios. We take care also of the vehicles outside of this box and drive the vehicles to the yellow entrances. And starting from the yellow entrances, you need to take care of the coordination of the vehicles towards the exit. And now there's still time to join us. So till April 10th, you can join us and win also some money and present your results at our workshop at the IB in South Korea. We have also several courses around our research and around the test bed, from bachelor's to PhD level, and everything is open. You can go and take the courses. And what else we are doing? Now I showed you the test bed. So we use the test bed as an incubator for new projects. I guess you know the competition of F110, and now we are working with Rahul on the next gen of F110. It should be more accessible, means cheaper, and the size should be also a little bit smaller. Now I showed you also our real-time experiments. Just to finish the presentation, I'm going to talk a little bit about how we were able, for example, to connect the test beds and how we were able to conduct reproducible experiments in our test bed. For this, we use the service-oriented architecture. An architecture in general is the organization of a system. On the left-hand side, we see a nice building, but it is static. So in software, we would rather like to have something dynamic, updatable, and so on. And if we look at today's function-oriented architecture and look at the example of Sense Plan Act, so they are implemented on software modules. The software modules are implemented on ECUs that are somehow connected. So the connections are, or the dependencies are hard-coded. And assume now we would like to update a module for the trajectory planning. And for this, we need to update many components affected from this update. And we propose the service-oriented architecture for software-defined vehicles. So assume you develop very nice algorithm for motion planning today and bring the vehicle to the road and ship it. And now you have a great idea to improve your algorithm. And in today's architectures, this is going to be very hard. So in our architecture, or in the architecture we propose, it's going to be possible. Just look at the example on the right-hand side. We see here an example of autonomous driving, and we are going to switch in a minute to remote operation because, for example, we are not going to proceed in our autonomous driving, maybe because we are going to a conflict which cannot be resolved by today's algorithms. And here you see the services. You can think of them as software modules realizing our autonomous system, now switching to the remote operation. This was, of course, an animation, but animation to convince you. I'm going to show you some results of our project. So there is a large-scale project called Unica Agile in Germany. We have more than 100 PhD students in this project, and we started at a white piece of paper, and after 5 years, we had 4 automated vehicles at level 4, and they were running our architecture. So look at this vehicle, for example, here driving. This is the so-called shuttle vehicle, and it uses our architecture. So in summary, I introduced you to our research in distributed predictive control. I showed you how we implement our research in real-time experiments, and showed you how we can how we provide an architecture, a service-oriented architecture for autonomous vehicles. What are the challenges in the next year? Just some keywords: mixed systems between, for example, connected and automated vehicles and human-driven vehicles. To be able to bring such systems to the road, we need to consider, of course, mixed systems. Of course, further research on data-driven and enabled systems is in nowadays, and we need to do more research on software-defined vehicles. At the end of my presentation, I would like to show some pictures of my collaborators. For example, at the top here, Christoph Steller from the EIT in Germany, and Katrin Flaskamp from the Saarland University, my collaborators from the GUC, Katrin and Oma. And here are some of 2 of my PhD students, and our chair of embedded software, Professor Kowalewski. Here is the vehicle from the project Unica Agile in the background. Is Andreas Malikopoulos. While I was visiting him at the University of Delaware, he is his nice testbed IDS-3C. Here is a picture from the visit of my PhD student, Julius Pervert, with the master student Lucas Hegerat to Rahul lab at UPenn. And here's a picture with my friend and collaborator, Ehsan Hashmi from the University of Alberta. With this, I want to tell you, collaboration is fun. Collaborate, and I'll be happy to discuss with you now and open the room for questions.
Thank you, Bassam, for the great talk. Let's open the stage for questions. You can either raise your hand and ask directly, or you can post a question in the chat, and I will read it for you. So maybe I'll be the icebreaker. I'm curious. So I'm sure you already had some of those applications, especially connected to the F110. Are you foreseeing some competitive rather than collaborative applications going forward? So for instance, racing or intersection managing, where people want to, you have different cars that want to have the precedence over others, as opposed to collaborative settings where actually everybody cares about the societal benefits and so on.
Yeah, absolutely. So in F110, we look at competitions, but of course the community is very inclusive and collaborative. So if you want to join the community, just email us and we can put you on our Slack. So the autonomous racing and the competition and collaboration between vehicles, this trade-off is very very interesting, and we want to make this more accessible. And that's why we are going to the next gen. So reduce costs and reduce size and make it more accessible. For competitions, also in our Olympics, which now is running, is more on the collaboration between vehicles. So we provide you with real world data, which we scale down to our test bed, and we take care of the vehicles outside of a rectangle. And once the vehicles arrive at the entrance, you are in charge on driving the vehicles. I hope this more or less answers your question.
Yes,
and I
yes,
hope
yes.
the internet connection was stable during the talk.
Yes, yes, it was perfect. I wouldn't have said it was through your phone. It was really good.
Oh.
All right, is there any other question for Bassam? Yeah, Scott, go ahead. I think you're still muted.
Yes,
Yeah.
thanks. Great talk. I enjoyed it a lot. What are some of the biggest challenges you see long-term in making work reproducible across these different test beds?
Actually, what we did, we proposed a service-oriented architecture to connect the test bed in Aachen with the test bed at that time in Delaware. And you could think if you implement such an interface once, you can implement it also twice and third and so on. But of course, there are a lot of things to consider in software. Of course, I showed you how it works, but maybe I need also to have some examples where it didn't work and where the vehicles were crashing. So software stability is a big issue. So this work was actually supervised by my PhD student, Patrick Scheffer. Maybe he can also comment on this with 1 or 2 words.
Yeah, I think it's hard to make experiments reproducible. So what we are trying to focus on is, we call it computational reproducibility. So assuming we were able to put down the vehicles at the exact same spot and they would behave exactly the same each time, then our uncertainties in computation time and communication time do not influence how the experiment turns out. So this is what we are working on. We think that we are able to control this with our architecture. This is a great point you're making. It's very hard to make it reproducible, even across, so even in one test bed, and even more so across multiple test beds.
Thank you, Scott, for the question. Any other question for Bassam and Patrick? Yeah, maybe I have a final one, which is, I discussed this with Andreas recently as well. So do you guys envision simulating and reproducing also infrastructure related properties? For instance, signalized intersections versus intersections with sensors, a bit in the style of the MCT in Michigan, for instance.
Yeah, this is a great point. We are working on this point in a project. One of my PhD students who is now on vacation, and we are using our test bed to create preliminary results for our large-scale experiments. And this is a project we are going to continue also with Ihsan at the University of Alberta. So the PhD student is going to visit Ihsan starting from April. And the idea or the big target is to create an architecture or let's say an interface between, not only between test beds, but also between test bed and reality. And of course, simulating some parts of the reality in the test bed is challenging. You are exactly talking about a paper we wrote for the next IV workshop, how to evaluate test beds, today's test beds, in relation to the reality. Which elements of the reality are already mapped in test beds? Which elements should be mapped? Which elements we cannot map? For example, what we cannot map is GNSS, Global Navigation Satellite System, signals, because the test beds are indoor and the signals don't arrive indoor. And we think that there is still some potential in linking the test beds to sophisticated simulation platforms and also to the reality.
Thank you. That's very interesting.
Great topic.
I look forward to
Yeah,
reading
we
it.
have a workshop on this topic at the next IV in South Korea.
Very nice. Very nice. Thank you very much, Bassam, for the great talk and also great outlook. I wish you all the best now that you are changing, moving to the south in some sense. And thank you all for participating. See you all for the next Autonomy Talk.